Welcome from my side to this next session, presenting one aspect of embedded vision. I want to show you how to use FPGA IP cores, off-the-shelf cores for camera development and embedded vision. Few sentences about sensor to image. We exist since 1989, a specialist for machine vision hardware, and started in 2008 with FPGA IP cores as standard products, not only for internal development, but also for reselling. And we are now doing a lot of projects around these machine vision protocols, GigaVision, USB Vision, Coax Express, where we have these IP cores. And since 2017, we are part of the Euresys group. As mentioned, my name is Matthias Schaffland. If you have questions later on, please contact me. What do I want to tell you in detail? First, I want to give you a typical overview about a typical architecture of an FPGA-based vision system to identify, where make FPGA IP cores sense at all. Then I give you an overview about available IP cores from our company, but not only, followed by the typical design flow if you use one of our IP cores to get an impression how that works in practice. And at the end, to give you some financial ideas, time to market considerations, what benefit not only from technical part, but also from timing part you get using off-the-shelf IP cores. Okay, how does a typical camera system look like? Yes, we have an image sensor somehow, one or even more, which is then connected to a processing unit. That could be an FPGA, that could be an SoC, maybe different things as well. And within that processing block, you need an interface to the sensor. That could be some SoCs have MIPI interfaces, for example, or for other sensors, you might have an IP core to do that, followed by some image processing, pre-processing, pixel detection, defect detection, something like that. And at the end, you need a way to output that image, or at least the results, to the next step of your processing machine. That could be Coax Express, GigaVision, USB 3 Vision, but it could be other protocols or interfaces as well. Typically, we have a kind of camera control within that block, which orchestrates somehow these processing blocks to get the correct results and to have an interface for an external interface as well. An embedded processor, so the counterpart is not too much different. So you have your external camera, which is connected to your processing system, processing board, which again could consist out of an FPGA or an SoC or an embedded PC or something like that. You need an interface to connect to the camera and implement the transport layer. In our case here, again, something like Coax Express, GigaVision, USB Vision, or could be MIPI and other interfaces as well. Then you typically have, again, an image processing block, which is then a little bit more than what you have in the camera. Here you do real image processing, analysis, AI, whatever, what you want to do. And the result is then used by the control unit and the machine interface to communicate with external systems. Short words about machine vision standards. The machine vision industry develops and maintains several standards for camera control and image transfer that started in 2000 with Camera Link, followed by GigaVision in 2006. Coax Express 2010, USB 3 Vision in 2013. All these standards are still under maintenance and are developed further. So we are not at the same level as 2000 or 2006. What challenges do we have with newer versions of these standards? There is a great demand for high data rate applications, so 10G or even 100G sensors get faster and faster. So these standards, if they want to be used for this kind of cameras, have to cope with that. But not only faster sensors, we sometimes have not only a simple 2D image, for example, we have multi-component data structures, which are used for example, in 3D applications or multispectral imaging. So these standards have to cope with it, multi-component data blocks and transfer them together. I don't want to talk too much about these standards in detail, just there's a trend, especially for GigiVision. Currently, you see a lot of cameras with 5G, maybe some with 10G, but for further speeds, we need some modifications here. So the working group is working on remote DMA support so that we are safe for faster speeds like 25, 50, or 100G applications. Similar with Coax Express. Coax Express from its origin is a copper-based protocol. Here we exists an extension, so it could be used over fiber as well. And this again opens the door for higher speed, higher lane rate applications with 25G or even more per cable, per connection. Okay, what FPGA cores for device development? So device typically is could be camera, but could be also an embedded receiver. So here we have GigiVision for cameras and receivers, which is available at Sensor to Image in the current version. GigiVision currently has the version 2.2. USB 3 vision for cameras and receivers. We only have a camera core at Sensor to Image. Others may have a receiver as well. Coax Express for cameras and receivers is available at Sensor to Image, which helps you to design cameras using this Coax Express protocol, or even receivers, standard frame grabbers, something like that, or embedded receivers. Camera Link HS, I did not mention it before. This is an additional standardized protocol. This is available at third parties. For sensor interfaces, there are a lot of different interfaces in the market. I mentioned only a few. Sony IMX sensors are quite famous in the camera business. So here's the focus for sensors with sub-LVDS interface. We at Sensor to Image have an IP core to help you to integrate them into your FPGA-based application. SLVS EC, this is a newer protocol used by Sony and even invented by Sony. This is used for newer sensors. This is available at third parties. MIPI, meanwhile, joins the machine vision industry as well, I would say. So you have more and more applications where MIPI is interesting. Here we have a solution as well for FPGAs. In the past, FPGAs have not been the best choice to connect MIPI sensors, but that evolved over the last years and it's much better now. For image processing, we at Sensor to Image have no dedicated offering, but FPGA vendors typically have products called Video Suite or something like that, where they offer some pre-processing IP cores like scalar, color transformation, filters, and so on. So that could be licensed directly by the FPGA vendor. If that does not really help, you are, of course, free to develop your own logic inside a camera or embedded receiver. For that, some FPGA vendors offer high-level synthesis tools that enables you to write FPGA code in C or C++ language. This makes it easier for you to write own image processing functions, especially if you come more from the software engineering. These tools often have image processing libraries included, so you do not have to do it totally from scratch. You can reuse image processing libraries and go on with your specific things. The output is typically an IP core again, so you can use it in your design flow as a typical IP core. How does a typical camera reference design looks like with an IP core from sensor to image? On the right side, you see the typical architecture, and matching that, it's very similar. So you have an external sensor, could be connected via an FMC card to an evaluation board or something like that. Within the processing part, we use an FPGA. So with an embedded CPU system, that could be a microblaze controller, an IOS, an ARM system, depending on the FPGA technology. Typically, the CPU system comes with a number of IP cores from the vendor, for example, for I2C or SPI or memory controller or something like that. So this is nothing what we have to reinvent. We simply can use them. And on the CPU system, typically there is running an application, what is delivered as C code to you, so you can modify and extend that, and a lower level library which handles the protocol, typically the control protocol. The streaming itself typically is done fully in hardware, in FPGA logic. So in a reference design, either we have an IP core to connect to an external sensor, or we have a test pattern generator followed by a frame buffer or something like that, and then the implementation of the actual transport layer, like GigaVision, USB Vision, or Coax Express. An embedded processor looks, at least from the block diagram, even a little bit simpler. We have our external camera, off-the-shelf camera from whatever vendor, which is connected to the FPGA via Coax Express or GigaVision. Here we have the corresponding transport layer IP to decode the GigaVision or the CXP streaming protocol, and forward some messages to the CPU system if needed, which is very similar like in a camera. So you have a device-specific application here, especially camera control. And in a reference design, what we deliver, the received stream is, for example, forwarded to a display controller, so you can simply see the image on a HDMI monitor or something like that, and directly see what is going on. What is the typical design flow with our IP cores? In the initial phase, we try to find a common development platform with an FPGA as close as possible to your final hardware architecture. So we typically use FPGA vendor boards, or if this is not helpful, we have our own machine vision development kit, MVDK, to have a common platform. Based on that platform, we deliver a full working reference design on that board, including necessary interface cards, for example, CXP, FMC cards. A normal evaluation board does not have these CXP interface. And on this reference design, we do an initial training to explain you how that works, what you have to modify for your final application, how to port that to the final hardware. In the implementation phase, which we support, you do the port of the reference design to your final hardware. In camera use case, you integrate your sensor control and readout logic. That could be an additional IP or not. and you integrate your product-specific image processing function, pixel operations, laser line extraction, whatever what you need. In case of an embedded processor or processing board, you have to do the camera control, dependent on the package and the logic. Genicam can be used, but if it's very specific, then maybe it's more hard-coded. And the main thing is that, of course, you integrate your application-specific image processing functions. Yeah, to give you some arguments why to use IP cores, some typical tasks you have to do when doing everything from scratch. Development of a basic vision transport layer IP core. If you really know what to do and have a clear picture what your IP should do at the end, this is at least 6 months of work, of initial work, but with ongoing maintenance work as well as the standard evolves. And if you have an IP, there might be additional feature requests and so on. So there's an ongoing maintenance work you have to consider. On the other hand, if you use a reference design, including the IP core, the effort to move that, to port that to your hardware is somewhere in the range of 1 to 2 weeks. Of course, dependent somehow on the knowledge and how close it to the reference design. But this is much shorter than your own development. On the sensor side, it is very similar. Example here, if you do an SLVSEC IP core or interface for your sensor, this again will take several months to implement that. And if you use an off-the-shelf IP core for that, it's again in the range of 1 to 2 weeks. The integration of the pixel pipeline, the image processing, this is highly dependent on the requirements, so I cannot give a general guideline or rule here, but typically this is anyway the main differentiation criteria to other products. So in our experience, this is where the camera manufacturers and so on should focus on and have their own specific know-how within that block. Only a few common things could be reused as IP cores, as mentioned before, using HLS or some video suites. But if you have special things, this is really your own know-how on IP. So as a summary, without IP, you have at least 1 year with at least 2 persons full-time working to make only the firmware part of the design. And with IP, there's the potential to reduce this initial development time to 1 to 3 months. On hardware side, this is a different topic. This is very similar. Later on, AMD Sightings will have a speech where you can use hardware IP and reuse that. So this might be interesting as well. Okay, I think 2-3 minutes left for questions. Thank you.
Thank you, Matthias. And if you have any questions, just use the Q&A section and we will answer them. And the first question is already here. What FPGA support do you support with your IP?
We support Xilinx FPGAs, Intel FPGAs, and starting now with even PolarFire FPGAs. Here we see the most market demand in the moment, but we are constantly watching the market and the demands and would do other things as well. In the moment, there's a lot of movement and some startups are coming up in the FPGA market. So this is interesting. But as mentioned, it's not only for you a lot of work to keep an IP core up to date. It's even for us a lot of work, and having a new FPGA technology is nothing what we do within 20 minutes or so. This is work as well. And of course, there has to be a reasonable demand.
Mm-hmm. And there's a question about what skills are expected from the core integrator?
This is nothing, or these are development tools. IP cores, you have to know somehow how to work with FPGAs. And you have seen that in the block diagrams. You have CPU systems, you have maybe memory, you have these actual IP cores, some firmware development inside the board. And so that requires at least an experienced FPGA person or team to work with that. We cannot support you in fully doing the FPGA design. We focus on the FPGA cores and the technology behind, but this is nothing for pure beginners. That's the truth.